All right. Good
Yes, we can hear
afternoon.
you.
All right. Good afternoon or good evening or good morning. I'm Oluwatosin Ijaleye, and I'm grateful for this opportunity to just share a uh, briefly with us the physics of molecular imaging. Just want to let us know what molecular imaging entails and what it's. Presently, I'm a doctoral student in IPEM Medical University, China. Okay, so I'm talking on physics of molecular imaging. So I know that I will not have much to talk about because most of our speakers have really done a lot on the, but just for me to introduce us to what molecular imaging is. Like most of us, maybe in our biology in undergraduate days, in doing maybe our first year, second year biology, we are taught about the organization level of the body. We know we have starting from the cells to molecules to tissues to organs to organelles and to the organism itself. And now we are looking at the molecular imaging itself. And this is an aspect of medical imaging that deals with imaging the molecules using the materials around our molecules to get out specials or informations for diagnostics purpose. So molecular imaging is the direct or indirect non-invasive monitoring and recording of the spatial and temporary distribution in vivo molecular, genetic, or cellular process, which is used for the biochemical, biological, and diagnostic or therapeutic applications. And this is from the RAN, the Radiological Society definition. And also, these molecular images help us to indicate the presence of magnesiums in the body. And what are those things that can be used? Because we know that this molecular imaging can help us in visualization, characterization, and the measurement of this biological process at the molecular level and at the cellular level in human body. And we might be wondering, how is this different from the conventional imaging method that we know? The difference with the conventional imaging method that we know is this: the normal imaging method that we know deals with the normal, the bone, the preliminary level of the body system. But here, some materials like radio tracers, like our last speaker elaborated more on radiopharmaceutical radio tracers, are being used to image this molecular level of the body. And not just to image it, each radio tracers will determine, okay, this particular, I want to measure the kidney. They will look at what each molecule of the kidney are we looking at, produce a radio tracer with this and try to image it out. Okay, so I'll continue. So now, what is now the effect of these imaging structures? What happens? What is the effect for the clinical? In clinical imaging, we discover that it images we have the anatomical imaging, which is when we have the X-ray, the CT, but here the molecular imaging deals with the physiological system. It can physiological imaging, deals with chemical imaging, and it also deals with the functional imaging. And for instance, on my slide there, we see this is an example of an 18 fluorine FDG PET imaging. We can see from this, these are the signals of the 18 fluorine that has been given, which shows the particular point where the radiotracers have already gotten to, and they could be imaged out. I'm so sorry, I don't know why my slide is slow. Just one moment, please. Okay, so for the molecular imaging modalities, we have several techniques. We have the PET techniques, we have the SPECT techniques, and we have the MRI techniques, the optical imaging techniques, and we also have the ultrasound techniques. Those are the major imaging techniques that is being used for molecular images. And these images, they are based on the number or the density of the molecular signals, which depends on these techniques at the targeted biological process, or at the targeted biological system. Okay, so for instance, like I said earlier, this is a typical image of an MRI, and where my cursor is, where my pointer is, shows the image without contrast agents. We can see, but now look at this. When it was given an MPIO, an alpha PCAM image, we can see it shows a part. This is the image of the brain. It shows a part and a more enhanced image, and that's the function of molecular image. It gives you more information about the part that is being imaged. And this is an example of an optical image where they use some fluorescence substance, fluorescence material. Look at it when it was imaged without any substance, any materials, and look at when the same system, but the same mouse was imaged with various substances. And this taking the optical image using the fluorescence imaging. You can also use the bioluminescence imaging for this particular image. And look at this. This is a typical example of the SPECT. Our last speaker has really elaborated of what's a SPECT imaging. That's why I'm not elaborating on these images, just for us to tell us how it works in molecular image. This is a typical example of a mouse image of a SPECT, and we can see the notes where we can see the effect of this, of the radiopharmaceutical that has been given before imaging this mouse, which gives those images at that particular point. Okay, we can look at it. What are the advantages of these images? They have their advantages and they have their own disadvantages. For instance, an MRI is an eye spatial resolution, and in an MRI there is no tissue elaboration and penetration limits. It can penetrate the tissue, but it has some disadvantage, which is low temporal resolutions, which is low sensitivity, and also the high cost. It's very cost effective. It costs a lot to get an MRI machine. And also the PET imaging is very high sensitivity, no tissue penetration limits. It can be quantitative, you can quantify it, and also it can also undergo a whole body scanning. There's no limit to which part of the organ you can image, and it also has a high temporal resolution. But one of the main disadvantages of PET imaging is radiation, because just like our last speaker explained to us, what will be given to the patients involves radiation. The machine is involved radiation, so patients are more exposed to radiation. So that's one of the disadvantages of PET imaging. And also for a photoacoustic imaging, which also has to do with it has high sensitivity, it has high spatial temporal resolutions, and it also has poor tissue penetration at short wavelengths. And the optical imaging, which some of us might be thinking, it's also an example of optical imaging is the near infrared imaging. It has high sensitivity. It has multiplex capability, meaning that it can combine with some other equipment at the same time and helps imaging. Also, it also helps in surgical guidance, and also high temporary resolution, but it has poor tissue penetration. You can see the various disadvantages and advantages of these various modalities in molecular imaging. And also this table also is also a brief summary of what the major molecular imaging devices do. And here we have the techniques, which is the SPECT. We have the tracers and probes that are being used. We have the signal detection, which concerns us as physicists, the sensitivity level, then the preclinical studies, which talks about the spatial resolutions, which are mostly calculated with the physicists and by software being developed, and also the temporary resolution advantages, as I mentioned a lot. But most importantly, I want to understand that for a PET imaging, it uses an high energy and also use a gamma rays, and also for a SPECT, it also uses low energy with gamma rays. And we can see that for an MRI, it uses radio frequencies. I know that in the next various lectures we're going to have, I know that we'll be talking about NMR and also MRI. We'll know more about the physics of this MRI, that majorly it is about radio frequencies and also waves, also with electromagnetic waves that has also been mentioned by our various speakers. Also for the optical imaging, I mentioned earlier on, it uses the bioluminescence and the fluorescence probes. That is what is given to the human or to the animal, and using the signal detected is detected by the light, like with the near infrared imaging. And ultrasound, all of us know ultrasound, it's also done by the ultrasonic waves. And these, each of them has their own sensitivity level. Like we can see the PET has a 10⁻⁻15 sensitivity level. I know that if we get these lights, we can as well study what's going on this table and we understand more. And for a molecular imaging, and also for in our so-called radiation oncology, which are the people that make use of molecular imaging alongside with oncologists, we have the three block processes, which is the molecular imaging. That's the first step to get the image out from the human body or from the molecular level. And after then, we don't just stop at just getting this image. And that's why we come in as radiation physicists, or we come in as medical physicists. We do the molecular signature determination. We want to determine, okay, what is in this molecule? We have some various softwares that can be used at this for the molecular characterization of the tumor. Okay, this particular tumor has been detected, maybe on the lungs. They characterize the tumor, what type of tumor it is, like we've learned in the previous lecture, it will be known. Then after this, after they determine what type of tumor, the molecular characterization of the tumor has been done, then they go ahead to the molecular therapeutics. And at this molecular therapeutics, then ionized radiation are being used to initiate specific molecular events, either to treat this particular tumor. So this is the three block process that is being involved, and a radiation physicist is being involved at this particular level. And what are the advantages? What are the advantages of molecular imaging to a radiation oncologist, or to a radiation physicist, or to a medical physicist? Number one, it improves the detection of tumor cells. Compared to the conventional imaging method, it improves the detection of tumor cells. We can say, okay, this is part, it is easier for us to be able to differentiate whether it is a malignant tumor or a benign tumor. It's easier for us to understand, okay, which type of tumor, which part of the body is being spread, because we get specific information from the image that we get from it. And after the characterization, so many other factors have been extracted from the information. And this information also helped us also to get a better and specific detection level of the tumor cells. Also, it also accurately defines targets and dose regime for individual patients. It is molecular imaging. Many of us, I don't know, most of the senior people here we know that now the world is looking into personalized medicine, and that's what's brought about molecular imaging. Is one of the things that is leading to personalized medicine. After detection, it helps to say, okay, this target, we can determine this particular dose. Okay, this amount of dose can be given. We can also determine, oh, this it helps us to go into individual patients. Okay, specific those planning for a particular patient, and also helps to define targets, not just in the case of just palliative care. No, okay, this is the target you are looking at. It helps, and which helps us, which reduce the effect of radiation on other parts of the body. And also we have the direct monitoring of the radiation delivery accuracy. We can use the molecular methods. We can use these methods to monitor the radiation delivery accuracy, whether it is being delivered accurately or not. And this diagram is just a brief workflow of a radiation oncologist, which also concerns a radiation physicist. Okay, what are the applications? What are the applications of these for us? Also, I said initially, physiological distribution of the pharmaceutical has a molecular base. We should know that. Also, signal intensity in magnetic resonance imaging. For MRI, is signal intensity we look at and say, okay, the signal intensity at this particular level is high. Okay, if signal intensity is high, as just of the contrast agent that is being given, okay, maybe that particular point is the imaging method. And I don't want to bother us more on an advanced point of this. Such different kind of these things have as biomarkers. These molecular imaging use biomarkers. Such biomarkers are maybe the tumor hypoxic. Such biomarkers are also acidosis. Okay, what is the acidic level of the tumor level? Such are the biomarkers that is being used. Okay, some biomarkers are also the protein level, the genes. The molecular level imaging can determine the genes. Okay, what are the genes that's found at this particular point? Then we can determine, okay, this gene relates with this particular disease and it can help us. And also direct monitoring of radiation delivery accuracy, I've said that earlier on. Also, it helps in early detection and treatment of diseases and basic pharmaceutical development. It can help in the pharmaceutical development. It's okay when a particular a new type of cancer tumor is being developed at a particular molecular level. The calculation of that molecular level can help people, the pharmacists, to go into the labs and say, okay, for this particular, we discover this particular chemical. It can help them in pharmaceutical development, which also helps the medical physicist that is also in the nuclear medicine department to say, okay, oh, we can apply this particular new developed pharmaceutical for this particular tumor that is being detected. And also, it also helps us in quantitative testing and imparting a greater degree of objectivity. And which one of the images is the MALID, which is the molecular imaging that is based on mass spectroscopy. Our speaker yesterday mentioned a lot on this when they were talking about what are on the clinical engineering's impact on as a physicist. Okay, now I just want to give us, just was open eyes, just pick one of the methods, just on PET. That's why the fact that of all these that I've mentioned, we still have a physical and technical limitation to PET imaging. And what are some of them are listed here, which is the related loss of contrast for small objects due to the partial volume effect, degradation due to attenuation, due to the atom effect, due to the scattering effect, and also to the sampling. Also, we have the arc effect, and we also have the depth of interactions, and we also have the variable background activity and the organ and patient motion. All these limitations can be overcome if we as physicists, we as medical physicists or radiation physicists can sit down and look, okay, how can I solve this problem? There are problems, there are limitations, and these are technical limitations. They can be solved by developing either a new equipment or by developing a software that can overcome, that can help us to bypass these, reduce the effect of these limitations and get a better signal. And the figure here shows a PET scan of the brain, and this is the tumor, and we can see this is the compound block in various dimensions at the coronal level, at the lateral level. Okay, now I want to briefly talk about the molecular imaging and the use of the targeted radiolabeled tracers. I won't go, I've said earlier, the last speaker mentioned a lot about this. I just want to tell us what happens at this stage is a 3-stage for the molecular level. The designs of molecules that can target specific soluble or immobile cell receptors, which are called ligands in the body. That's the first stage. And after this stage, then we now go to the attachment of radioisotopes that can emit photons without changing the biological binding properties of the target molecule. Don't forget, we should remember that molecular imaging is based on targeting molecules in the body. So after we've designed the molecules that can target specific soluble in this particular body, which is called receptors, or we can call them ligands, then we look at, okay, what radioisotopes that can be attached that can emit photons at this particular, because the equipment we want to use, especially the PET and the SPECT, use photons, they use gamma rays. So we need to attach a radioisotopes. And we must also be careful that the radioisotope being attached must not must not change the biological binding properties of the target molecules. And the final stage is the injection and the in vivo imaging using high resolution and high sensitive device, such as the optical imaging, the ultrasound, the SPECT, and the PET. And also, PET allows us to quantitatively and accurately detect the molecular target of radioisotopes, which determines the tissue biological properties of processes. And commonly, it helps us to perform glycolysis or cell proliferation. It also involves the tomophysis. And okay, now we can ask ourselves this question: as a physicist, how can I fit in? We can fit in dose optimization. We can help in optimizing dose to get the accurate dose, because like we know, like previous speaker mentioned, medical physicists are the ones that plan dose, the amount of weight for a part after it has gone for imaging at the CT level using the MRI, using this equipment. With the medical physicists are also there to determine dose. So our work is to determine, to optimize the dose for the children pediatric imaging, and also at the adult imaging, to image wisely to avoid the dose minimizing the dose on the body that's organ at risk. Also, image optimization. We have various softwares that we can use to image for image optimization. After the image has been got, it's been exploited into softwares for image optimization. I must tell you, most of these softwares are being developed by physicists that sat down to study, okay, what are these machines? Okay, this is the image we are getting out using physics concepts. And then we can input our images into these softwares and we get the image optimized. Also, development of software algorithm can be detected, and these algorithms will help us in advancing the sensitivity and the spectral temporary resolution. We see that when we are considering the disadvantages, we discover that some of them have temporary resolutions, some of them has low resolution. As a person, you can think, as a visitor, you can think, okay, what software algorithm can I develop to get this to increase the sensitivity of this particular image? Also, physicists can also create new camera geometries for special biomedical applications. Also, we can also understand the physical system, which comprises the subject tissue, the radiation transport, the imaging system. Most of these have been done by those that are into biophysics, and also radiation, and also physicists, and also to provide the best available imaging quality and quantitative accuracy, which is very important for our dose planning and for our treatment planning. And also, we can do image reconstructions. Image reconstructions are done using applications like Python, like MATLAB. Some people also use that, and I know we'll still talk about the artificial intelligence in physics. These are some of the things that we'll learn about. Also, signal processing. We've gotten the images. We can also help in processing the signal. That's where we physicists fit in molecular imaging. Also, image processing and data or image analysis algorithm. We can develop algorithms, and also we can design sensitive sensors for these materials. We can update and improve their sensors. Okay, I've been mentioning software. So these are relevant softwares in image analysis, and all these softwares that are listed out here are open source. You can get them. They are free. We can get them if we want to lay hands on such imaging software to practice. And most of the common that I use majorly, I use Imageje majorly. I also use the VTK, and I also use the ITK and the OpenCV. They are very good software for image optimization and for signal processing. What to ponder on as undergraduates, as postgraduate students? We can learn. Molecular imaging might not have been so advanced in Africa, but we can learn. We can read on these emerging medical imaging devices. We can learn more about it and see how we can fit Also, we can make ourselves relevant by studying the basic computing tools, which is the Python, the MATLAB, the C++. Many of us in undergraduate days, we did C++, we were introduced to C++, we were introduced to Fortran. It's not a waste. Those skills can be used to develop algorithm in medical imaging for optimization of images, which will be relevant, and peradventure, one day, one of our names can be on the imaging tools that, oh, so person from Africa developed this imaging tool, tool for us to optimize image. Also, you can have a grasp of the analytical tools that are listed there. You can go online, check those imaging tools and see most of them have manuals that we can go to. Okay, how can I also improve? And also, we can also develop post-processing software, which is relevant to Africa. Because one thing I've understood in my course of study here is also that we also have differences when it comes to our body mechanism. When it comes to DNA, we know that DNA varies from one person to the other. And so also this experiment also varies from one place to the other. So also Africans, as Nigerians, we must also look at it and say, okay, how can I develop a post-processing software that is relevant to what the information that is gotten from patients from this image, not just basically focused on what has been developed in the Western world. Thank you. So with this, I come to the end of this presentation.
Thank you very much, Ma, for that presentation. Molecular imaging, physics of molecular imaging. I believe this is a budding field that will probably go places. Actually, I just a few comments. I don't know. Would you like to say molecular imaging is quite related to nuclear medicine?
Yes, it's related, because the major equipment used are part of the equipment used for the imaging level is the nuclear medicine equipment. Is related. It's just that it goes a step further. It goes a step further by using contrast agents, specific contrast agent for specific molecules.